Okay, welcome everyone. Today we're diving into something pretty fascinating, starked you could say, by the spirit of builders, like MIT's Professor Patrick Winston. You know, the guy who loved making things wood, metal, rocks.
And code, especially code.
Exactly. And that leads us to this question. Have you ever wondered how a program could not just do something complex, but then actually turn around and explain why it did it, or how it got there?
Yeah, it's not just about function, it's about transparency, maybe, understanding.
Right, making the machine understandable, not just effective.
And that's really our mission today. We're going to explore some really foundational ideas from early AI. We're talking goal trees, rule-based expert systems, stuff like that.
Sounds a bit technical.
Well, maybe the names are, but the concepts, they give you these surprising insights, not just into AI, but like how we solve problems, how human intelligence works, even storytelling. You might have a few haha moments today.
Okay, I'm intrigued. So where do we start with programs explaining themselves?
A great place to start is an early AI classic, Terry Winograd's Block's World program. This was back at Stanford.
Block's World. Okay, what did it do?
So imagine a simple virtual world on a screen with different colored blocks. You could tell the program, put block B2 on top of block B7.
It would just stack them.
Yeah, it would figure out how to do it. But here's the kicker. After it did something, you could ask it questions about what it just did.
Like what?
Like, why did you clear the top of block B1? Or maybe, how did you manage to put B1 on B2?
Whoa. Okay, so it wasn't just following orders, it was aware of its process.
Yeah.
How did it do that? What was the secret?
Well, the secret, essentially, is that it didn't just act and forget. It kept a record. It left a kind of trace of its actions. And this trace was structured as something called a goal tree.
The goal tree.
Or sometimes you'll hear it called an and/or tree. The basic idea is to achieve a big goal, like put B1 on B2, the program breaks it down, into smaller, simpler sub-goals. And it keeps track of how these goals relate. Sometimes you need to do all steps A, B, and C to achieve goal X. That's the and part. Other times, maybe you could do step D or step E to get there. That's the or part. It maps out its own logic.
So it's building a map of its own thinking process as it goes. That makes sense for the how. But let's take that example. Put B1 on B2. What does that breakdown actually look like? It's not just one step, right?
Yeah, not at all.
It's got to think, okay, find space, grab the block, move it.
Exactly. For put on B1, B2, the first level might be find space on B2, grasp B1, move B1 over B2, and ungrasp B1. 4 basic steps.
But what if, say, B1 isn't clear? What if there's another block, let's call it BX, sitting on top of B1?
Good question. That's where the tree gets deeper. The grasp B1 step can't happen yet, so it generates a new subgoal, clear top of B1.
Okay.
And that goal might require another subgoal, get rid of BX.
And how does it get rid of BX?
Well, it might decide the best way is to put BX on the table. And guess what? That triggers another whole sequence. Find space on the table, grasp BX, move BX, ungrasp BX.
Wow. So it's like these nested Russian dolls of goals?
Precisely. It's recursive, simple actions calling other actions, which might call others, creating this potentially complex web, but it's all perfectly logical and crucially traceable.
So that's the goal tree, this detailed record.
Yeah.
That's what lets it answer the why and how questions.
Exactly right. The goal tree is its memory, its internal narrative, you could say. So when you ask a why question, like why did you get rid of BX?
Yeah.
The program just looks up one level in the tree structure it built. It says, well, because I was trying to clear the top of B1.
And if I ask why it cleared the top of B1?
Up another level, because I was trying to grasp B1. And eventually, because you told me to put B1 on B2.
Got it. And how questions?
How questions go the other way down the tree. How did you put B1 on B2? It looks at the immediate subgoals. Well, I did it by doing these 4 things. Finding space, grasping, moving, and ungrasping.
Yeah.
You could then ask, well, how did you grasp B1? And it would go down that branch.
That's actually really elegant. It explains its reasoning by retracing its steps on this map it made.
It is elegant. And it connects to a really neat idea from Herb Simon, Nobel laureate, brilliant guy. He had this thing called the ant metaphor.
Yeah, metaphor. Okay.
Imagine watching an ant walking on a sandy beach. Its path looks incredibly complicated, right? Zigzagging all over the place.
Yeah, you'd think it had this complex navigation plan.
Right, but Simon's point was maybe the complexity isn't in the ant. Look closer.
It's just walking around pebbles and stuff.
Exactly. The ant itself might be following very simple rules like if obstacle, turn left. But the environment, the beach with all its pebbles and slopes is complex. So the interaction creates the complex path.
Okay, I see the connection.
The apparent complexity of the blocks program with all those nested goals, it's not necessarily because the program's code is super complicated. It's mostly because the problem it's solving, the specific arrangement of blocks, the environment is complex. The program's relatively simple rules just react to that complexity.
So complex behavior doesn't always mean complex internal rules. It can be simple rules in a complex world.
That's
Yeah,
what I
yeah,
meant.
that's a big insight.
It really is.
Okay, so that's programs explaining actions. But you mentioned these principles also led to something else, rule-based systems.
Right. Fast forward a bit to, say, the mid 1980s. There was this big commercial push for AI, and one of the hottest things was rule-based expert systems, or RBES.
Expert systems.
Okay, the core idea was let's try to capture the knowledge of a human expert, but break it down into really simple if-then rules.
If then, like programming.
Sort of, but focused on knowledge representation. Like, if this condition is true, then that conclusion is also true. Or maybe, if you want to achieve goal Y, then you should do action Z. All the experts know how, distilled into these little conditional chunks.
Can you give an example? What were they used for?
Oh, lots of things. One famous early one was ICIN. It was designed to help doctors diagnose bacterial infections.
Wow. Okay, that sounds complicated.
It was, but we can simplify it. Imagine instead of diagnosing infections, we're trying to build a system to identify animals in a small zoo. Just a few rules.
Okay, a zoo identification system. I like it. How would that work?
So we feed it rules, maybe something like, Rule 1, if the animal has hair, then it is a mammal. Simple enough.
Yep, makes sense.
Rule 2 might be, if the animal has sharp claws, sharp teeth, and forward-pointing eyes, then it is a carnivore.
Notice the and D there needs all three.
Exactly. It's like an and gate in logic. We could also add an observation, maybe not a strict rule, but evidence. If it eats meat, then that's more evidence it's a carnivore.
Okay, so we've got mammal, carnivore.
Mm.
How do we get to a specific animal, like, say, a cheetah?
Another rule. Rule 3, maybe. If it is a mammal and it is a carnivore and it has spots and it is very fast, then it is a cheetah.
Got it. So the system takes facts, it observes.
Right. This approach is called forward chaining. It starts with the known facts. I see hair, I see sharp teeth, it has spots, and it works forward through the rules.
Firing off conclusions.
Exactly. Has hair triggers mammal. Sharp teeth, claws, forward eyes triggers carnivore. Then mammal, carnivore spots, fast altogether trigger cheetah. It chains forward from evidence to conclusion.
And you said these were called expert systems.
Yeah.
Did they really think like experts?
Well, that was the marketing. In reality, they often reasoned more like, well, novices following a checklist. They only knew the explicit rules they were given. They didn't have the intuition or common sense of a real human expert. If a situation wasn't covered by a rule, they were stuck.
I see. But, like the blocks program, could these rule systems explain their reasoning? If I asked why it concluded cheetah.
Absolutely. Because that network of rules, if hair then mammal, if claws teeth eyes then carnivore, if mammal carnivore spots fast then cheetah, it implicitly forms another kind of goal tree, an inference tree.
Ah, okay. So asking why cheetah would trace back through the rules it used.
Precisely. It would say, because it's a mammal, a carnivore, has spots, and is fast, ask why carnivore, because it has sharp claws, sharp teeth, and forward-pointing eyes. It can justify its conclusions by showing the rules it followed.
Makes sense. Is there another way besides forward chaining?
Yes, there's also backward chaining. Think of it like this. Forward chaining is like a detective finding clues and seeing where they lead.
Okay.
Backward chaining is more like Othello. The detective has a suspect in mind and works backward to see what evidence they need to confirm it.
How does that work with the cheetah?
You'd start with a hypothesis. Is this animal a cheetah? The system then looks at the rule for cheetah and works backward. Okay, if cheetah, then it must be a mammal, carnivore, have spots, and be fast. Then it thinks, okay, how do I confirm carnivore? It looks for rules concluding carnivore and works backward again. To be a carnivore, I need to check if it has sharp claws, sharp teeth, and forward eyes. It only looks for the specific facts needed to prove or disprove the initial hypothesis.
Ah, so it doesn't just gather all possible facts, it's more directed.
Exactly. It's often much more efficient if you have a specific goal or question in mind. It doesn't waste time exploring irrelevant rules.
That's pretty smart. Were these systems just academic, or did they, actually get used for real things, besides ICN?
Oh, definitely. There are some amazing success stories. One I really like is Jose Duarte's PhD work at MIT in the architecture department.
Architecture, using rule-based systems.
Yeah, he built an expert system designed to generate house designs in the very unique, complex style of this famous Portuguese architect, Álvaro Siza.
No way. How could rules capture an artistic style?
Apparently, quite well. Duarte encoded Siza's design principles as rules. The system took user requirements, room sizes, relationships, site constraints, and generated Siza-like floor plans.
And the punchline.
The system got so good that Duarte actually mixed some of its computer-generated designs with real Siza designs, showed them to Siza himself, and Siza couldn't reliably tell which were his and which were the program's.
That's incredible. The program passed the Siza Turing test.
Kind of. It really shows the power of capturing even complex, seemingly intuitive knowledge and rules if you do it right.
Okay, but how do you do it right? How do you even get that knowledge out of an expert's head and into rules? Siza probably couldn't just list his design rules off the top of his head.
Exactly. That's the whole field of knowledge engineering. And there are some really practical tricks or heuristics for doing it. These are gold star ideas, honestly, and they're useful even just for learning things yourself.
Okay, lay them on me.
Oh.
What are these heuristics?
All right, heuristic number 1. Deal with specific cases. Don't ask the expert for general rules. They often can't articulate them well, or they forget exceptions.
So what do you do instead?
You watch them work on or talk about very specific examples. Let's go back to grocery bagging. If you ask a pro bagger, what are your rules? They might say, heavy stuff on bottom, light stuff on top. Very general.
Right.
But if you hand them a carton of milk, then a bag of potato chips, then a can of motor oil, then a jar of olives, you'll see them apply very specific, maybe unstated rules for each item. Milk goes here, chips always on top, motor oil needs its own bag. You elicit the rules through concrete examples.
Okay, makes sense. Confront them with the details. What's number 2?
Number 2, ask about things that appear to be the same but are handled differently.
Okay. Like what?
Stick with the grocery analogy. To you, maybe frozen peas and canned sweet peas are both just peas. But the expert bagger might put the frozen ones in an insulated bag and the canned ones just anywhere. You see this difference and ask, wait, why did you treat those peas differently?
They'll say,
Oh, well, this one is frozen. It needs to stay cold. That one is canned, shelf stable. Boom. You just uncovered crucial distinctions, frozen, canned, that are part of their internal rule system. It gives you new vocabulary for your rules.
finding the hidden categories by looking for inconsistent handling. Clever. Okay, what's the third one?
Number 3, and this is maybe the most powerful, especially for programmers, build a system and see when it cracks.
Just build it and break it.
Pretty much. Take the rules you've gathered so far, implement them in a program, and then start feeding it test cases, especially tricky ones. When does it fail? When does it give the wrong answer? Or just stop, confused?
And that tells you.
It tells you exactly where your rules are incomplete or wrong. The point where it breaks highlights the missing piece of knowledge. It's incredibly direct feedback.
That sounds a lot like just learning anything difficult.
Yeah, it is. Think about doing a hard problem set in physics, or learning a new language, or figuring out a complex piece of software. When you get stuck, when you hit a wall.
You've found a gap in your understanding, a missing rule in your own head.
Exactly. That frustration is actually valuable data. It's telling you precisely what concept or rule you haven't grasped yet. It's like running an experiment on your own learning process.
Build it and break it. I like that.
Yeah.
Okay, so we've got these systems, goal trees explaining actions, rule systems making diagnoses, even designing houses. They seem pretty capable. But what does it all mean? Are these things really smart, like humans are? Or is something missing?
That is the critical question. And often the answer is that these systems possess what you might call a thin veneer of intelligence.
Thin veneer, meaning?
Meaning they can follow the rules, they can perform the task based on the knowledge explicitly given to them, but they often lack deeper understanding, context, or just plain common sense.
Can you give an example of that veneer cracking?
Sure. Think about a rule-based grocery bagger. It might have the rule, put potato chips on top.
Right, we established that.
But why? Does the program know it's because chips are fragile and crushing them makes customers unhappy?
Probably not. It just knows the rule.
Exactly. It doesn't understand the reason behind the rule or the consequences of breaking it. It just knows if chips then on top. And there are more dramatic examples. Remember MYCIN, the medical diagnosis system?
Yeah.
During debugging, apparently, it once calculated a dosage and recommended A barrel of penicillin for the patient.
A barrel? Seriously?
Seriously, it followed the rules for calculating dosage based on infection type and patient factors, but it completely lacked any real-world sanity check. No sense of proportion, no common sense that a barrel is, not a medical dose. That's the veneer cracking.
Wow, a barrel of penicillin. That perfectly illustrates the missing common sense layer. Okay, so these AI systems have limitations. But does that mean rules don't play a part in our actual human intelligence? In our common sense?
Now that's where it gets really interesting. Because evidence suggests that implicit rules are a huge part of how we understand the world, even if we're not aware of them.
How so?
There's a great demonstration using what are called story elaboration graphs. Take a story everyone knows, like Shakespeare's Macbeth.
Okay.
A very short summary might explicitly state, Duncan is murdered by Macbeth.
Right.
But does that summary ever explicitly say Duncan is dead?
No, but obviously you know he is.
Exactly. You know it instantly. Why? Because you have an implicit rule in your head. If person is murdered, then person is dead. The story doesn't need to state the obvious because it relies on you applying that rule automatically.
Huh. Never thought of it that way.
Or think about why Macduff kills Macbeth at the end. The play shows Macbeth killing Macduff's family, but does it explicitly state Macduff was angry and sought revenge?
Not in those exact words, no. You just infer it.
Right. You infer anger and revenge because you have implicit rules like, if family harmed, then person is angry. Or if person is angry at killer, then person might seek revenge. We fill in the blanks using our own internal rule book.
So these story graphs, they show this.
They visualize it beautifully. You have a few white nodes representing the explicit facts stated in the text. But connected to them is this vast network of gray nodes, all the stuff we infer using these common sense rules.
Or gray than white.
Often vastly more, especially in complex stories like Hamlet. Because everyone is related, one action like Claudius killing King Hamlet triggers cascades of inferred emotions and motives across many characters based on relationship rules. If father killed, then son is angry. If husband killed, then wife might be complicit or afraid, etc. A few explicit facts generate enormous amounts of inferred information.
Wow. So our understanding is mostly inference, built on top of the explicit facts.
Which leads to this really profound idea about storytelling itself. You could say that storytelling is largely a matter of controlled hallucination.
Controlled hallucination.
Yeah. The storyteller doesn't have to spell everything out. They just need to provide the right explicit triggers, the white nodes. They rely on the fact that you, the listener or reader, have this massive network of implicit rules already built in. They give you the seeds, and they trust your mind's rule-based system to hallucinate the rest of the rich, detailed picture, filling in the motivations, the consequences, the unspoken context.
They're leveraging our own internal expert system.
Precisely. They control the narrative by carefully choosing which of our internal rules to activate.
What a fascinating way to think about it. Okay, this has been quite a journey. We went from blocks, world programs, explaining themselves with goal tree,
Right, tracing their actions.
to these powerful, rule-based expert systems doing diagnoses, designing buildings.
Even if they needed some common sense sometimes.
Aha, definitely. And then we got these really practical heuristics for getting knowledge out of experts or just for learning better ourselves.
Yeah, those heuristic-specific cases, same but different, build and crack, they're genuinely useful.
So wrapping this up, what are the big takeaways for listeners?
I think there are two main things. First, this idea from Herb Simon. Complex-looking behavior doesn't always require a complex internal program. Sometimes it's just simple rules interacting with a complex situation or environment.
The ant on the beach.
Exactly. And second, maybe even more importantly, our own minds work like this too. Our intuition, our common sense, even how we enjoy stories seems to rely heavily on this vast, mostly unconscious network of rule-like inferences. We're constantly filling in the blanks, making connections.
We're all running our own internal rule-based systems.
In a very real sense, yes. Far more sophisticated and flexible than MYCIN, hopefully, but the principle is there.
So maybe a final thought for everyone listening to mull over.
Go for it.
As you go through your week, maybe pay attention. How many of your own daily decisions, your reactions to things, your interpretations of events, how many might be based on these kinds of unstated, deeply ingrained if-then rules you carry around?
What are your personal rules?
Yeah. What insights could you get if you actually tried to identify some of them? Might make you a little more self-aware, perhaps. We hope this deep dive gave you a bit of a shortcut there, and definitely something interesting to think about. Thanks for joining us.